Okay, so thanks everyone for joining me today to talk about applying AI in your organisation. As Sam said, I've been working with AI since the 90s, and I'm really privileged in EE to work with lots of skilled practitioners, and so it's great to have the guys joining me today as part of the panel, and I'm sure they've got lots of very interesting experiences and to talk through a bit later. What I'm not going to talk about today are the algorithms themselves. Okay, it's a huge subject. It's very kind of dependent on what you're doing at a given time, and I couldn't possibly cover it in the time. Instead, what I'd like to do is focus on pragmatically applying the technologies. And today is really about what to think about when you're developing, deploying, and operating anything with artificial intelligence or machine learning. What are the pitfalls and some suggestions for avoiding them? Okay, so AI, what is AI? AI can mean lots of things to different people. And you can get into some unproductive discussions about whether something's AI or not, is it intelligent or not. I take a pragmatic approach, which is that AI are, if you like, cognitive services, intelligent things, advanced computing services that do things like help you understand your data better, or they automate important tasks. Typical things that they do, machine vision, I think we're all aware of. That's where you're finding things in images. Here's a photo from one of our offices. It's an off-the-shelf algorithm. I think it's a Google one, and what it's done is it's picked out people and screens and chairs and all sorts of things automatically. A lot of AI is about that kind of turning unstructured data into something that you can kind of is more structured, more understandable. Natural language processing is part of that. The ability to turn lots of organizations have huge amounts of untapped documentation, PDFs and things like that. And if you could pull the data out of that, you'd get much better understanding of stuff. This particular example here is in that little box there. Is based on something called GPT-3, which is kind of one of the latest models in natural language processing. It took an awfully long time and a lot of compute power to compute that particular model, but it's been used for lots of really interesting applications. This one here actually takes some legalese and turns it into text that a 6-year-old or a 10-year-old could understand, which I think is a really useful application of AI. Robotics. So I think when people think about AI, often the thing they think about a lot is robotics, is robots. Of course we do. We're all waiting for more advanced robotics. I'm certainly waiting for autonomous cars and the like. Still a way off apparently. But there are lots of areas where it has been used. Mining is one of them. You've got a controlled domain effectively. It's dangerous, so it's a good place to have machines rather than people. And here's an example of an autonomous mining truck. It's got two little kind of antennas at the front there. If you look on the kind of these bits here, those are part of the sensor fit for driving the vehicle around. And this last piece here is kind of the more where you have kind of lots of organizations have huge amounts of data coming in. It's just too hard for a person to be able to process it, or the decisions that we're just not able to make. And so, there's lots of applications of AI to kind of automate decision making. So this is an example that we have here, where it's kind of effectively automating detection of suspicious kind of transactions in a business. So I'm going to go start with the principles here, or some principles. These are things that I've kind of picked up along the way. I hope they're useful to you.
Sorry, Simon. I'm just going to pause for a sec because I don't think the screen, the slide has moved forward.
It hasn't. It has on my screen. Which slide can you see?
What is AI?
Really? Oh.
That's okay. If you can,
I'll try again.
yeah, try again. Try again. It'll be fine. Yeah. Maybe just screenshot the whole thing. Yeah, thanks, Paul. That means we haven't done it.
That means we haven't done what?
I was just Paul was just saying you can't see anything, so I was just saying that's because it hasn't changed.
Can you see anything now?
So yes, we've got that now.
What can you see?
Key principles.
Okay, good. All right, let's see if this. Stop me if and we'll just have to do this per slide.
No, that's perfect. If you would just mention as you change slides, Simon, then we'll know whether or not to expect a slide change for a few slides.
Perfect, we'll do, Sam. Okay, so yeah, so these are principles here, things that I've picked up along the way, effectively. And the first one is that AIs are good at very specific, narrowly defined tasks. So we're still a long way from the sort of general intelligence that I dreamt about when I first studied it, and that people have, which enables them to transfer learning from one domain to another. So, for example, a program that is trained to play chess will not be able to play drafts. At the very least, if you want to take your chess program and get it to play drafts, you'd need to train it on new data, but probably you'd have to change the fundamental algorithm as well. The second principle is that AI is anything with AI machine learning is very data dependent. So you probably have lots of data, and you probably have lots of things in your organization that if it could be automated with AI, it would improve your business. And of course, for AI to work well, the data must be good quality in the traditional sense. It's got to be correct. The data is wrong, fundamentally wrong in places, then effectively your machine learning will learn the wrong stuff, and you don't want that. But you also have to have ground truth data, and that's data that has been labeled with the true result. In most cases, you need that. So if you have 1 million photos, that's great. But if your business is about needs pictures of cats and dogs in it, then you also have to have, to train the machine learning, you also have to have examples of, you have to label them with which ones have cats and which ones have dogs in. The last point there, the last principle I think is about performance, what I call performance, which is how accurate your algorithm is fundamentally. No system is 100% perfect, whether that's standard software or people make mistakes. And you do need to understand what level of performance will give you benefit. It's easy, I think, when you think, well, should I apply AI or not? So what level of performance do I want? And you say, well, 100% or maybe 99%. But it's going to be very hard to reach. And very often you don't really need this. So for example, for applications on large data where there's no way that it can be handled by people, your current baseline of performance actually might be close to zero. Nobody's detecting it, or very, very rarely. So if you had a true positive detection rate of 10%, that would be a tremendous improvement. One way of looking at this, I think, is if you have a need to find the needle in the haystack, then it can be very difficult. But if you have a use case that is about shrinking the haystack, then that's probably a really good one for application of AI. Okay, I'm going on to the next slide, Sam. Shall we see if this works? Can you see another one? Yes, okay. So those are some principles. I'm going to talk now about some practices for applying AI in your organization. First, by looking at the typical steps in creating a machine learning algorithm. Then steps required to integrate and operate that algorithm in your business. Okay, next slide. Is that good? Yeah. So let's start with the typical steps in creating an algorithm. So it all begins on the left-hand side here with a good set of data, which is hopefully labeled. If it isn't labeled, if it isn't ground truth, then you'll spend a lot of time doing that. Usually there's a initial period of exploration where you look at the data, you understand it, you maybe look at the distributions, the relations between single variables and the sort of outcomes that you're looking for, and any other statistics that come up. And you kind of get a feel as to what the data is. Does it look likely you'll be able to get the sorts of results that you want, and whether you have enough data to train the model. In most cases, the raw data needs some kind of massaging. It's very rarely that drop the whole data as is in front of a machine learning algorithm. If you do, you're kind of asking the algorithm to do a lot more work. And sometimes that's kind of, that can require some quite radical transformations to create features from which you think the algorithm can learn. So the next step, or usually actually you probably do these two round about the same time, is you select your algorithm. You work out what it is you want to do and then decide, well, is it a classification problem? Is it a regression problem? Am I clustering and segmenting things? Am I trying to do some kind of optimization? Take into account any other requirements, such as, do I need to be explainable? Is that a requirement for me? Do I need to incorporate some business rules that I already know? And then you train it on some of the data, on most of the data, in fact. And how long that takes really depends on the algorithm that you've chosen, the amounts of data that you have. It can be very quick. It can be, seconds, less than seconds. It can be minutes, or in some cases, it can be days or even weeks. It just depends. And then you want to test it. Then you want to test that algorithm. The important thing here is you test it on unseen data. That's data that it's not in the training set, that your learning algorithm's never seen before. This is very important. You can quite easily get 100% performance if you test it on seen data, but when you use it in anger, you won't get anything like that. It'll probably just revert to random or something. And at this point, once you've tested it, you can evaluate its performance. Do you need to, does it meet your performance criteria? Is it better than what you're doing at the moment? Is it an improvement? Is it better than just random, effectively? If so, you can deploy it. Otherwise, you'll need to go around again. Okay. Next slide. Thumbs up? Yeah. Okay. So now you've got an algorithm that you think is good enough, and you want to deploy it into production. I think at this point, I just want to raise something about development times and how long it takes things to run in operations. So they operate on different timescales. So it might take days or weeks to train an algorithm, but it could still be run in milliseconds. Okay, so don't be scared if you're thinking, it's taking me days to train an algorithm. It kind of depends. Sometimes it does, sometimes it doesn't. But it may well be the case that you're still able to run in the times that you expected it. So we have created our algorithm here, and now you want your data engineers to integrate it into your operations. So they have to find a way to take that algorithm and fit it into your ordinary kind of business software. And it might be, you might be lucky, you might be in a kind of a very modern kind of architecture, in which case you can deploy the model as a microservice. That's great. That usually works really well. It might be you're in something a little bit older and you have to do slightly different deployment mechanisms. Whatever it is, you've got to work out how to integrate it in, and you've got to work out a means of deploying this algorithm, so getting it from the development space into operations, hopefully repeatedly or repeatably. You should expect that the world around your business will change, and so you should expect that the data around your business will change, and that the algorithm performance will change. So you should always monitor what's happening in your algorithm, like taking data here and performance data and evaluating how well you're doing. And that's usually a couple of things. It could be just making sure that there's things around seeing if the statistics have changed of the operational data. Are they different from the kind of statistics of this historical data here? But also checking the results, which might be, sort of random sampling and doing some kind of comparing against a known oracle, so somebody or something that knows the correct result. Or it might be that you're fortunate and actually you can get the performance frequently, and you can have them running in something like an A/B testing regime. But the important thing is that you are monitoring the performance. I guess there's a question about how often you should deploy. What's the frequency of this, and I guess it really depends. So typical strategies can be, well, every time we train it, we deploy it, or it could be that you take something like an A/B testing or multi-arm bandit approach, in which you've got multiple models running at the same time, multiple algorithms running at the same time, and you're effectively moving your the one in operation to your operations to choose the one that is best performing. Okay. This slide here, I love this diagram. Can you see it, by the way? Have I moved? Yeah. Okay. I love this diagram from Google because I think it gives another angle on what I've just been talking about. It's a great graphic illustration of the work you need to do in making and deploying an algorithm, and it's originally from a 2015 Google MLOps paper. If you're experienced in using machine learning, it's very easy to focus on this box here, that's the hardcore code, that's the core of the algorithm, probably something in Python or similar, and worry about what's going on in here. You know, should I use an SVM? Should I use a random forest, and so on? But actually, to train a model and to get it to work well in operations, you have to do all this other stuff around it. You've got to collect the data, all the things we talked about earlier. You've got to bring it in from many sources, probably. You've got to clean the data. You've got to analyze and evaluate the output of the algorithm. You've got to validate that it works as expected, and keep measuring that performance and validating and evaluating. And so the implication here really is that, you know, when you are doing this stuff, you need a team that can cover all of these areas. So if you only have people focused on this central box here, then what you'll get is some very stressed data scientists, and it'll be very hard for you to get that algorithm into stable production or operations. So hopefully the previous slides have made it clear the need for data. I just want to underline again that, you know, creating your own AIs or machine learning is only possible if you have very solid data foundations. The data has to be good quality, it has to be ground truth, and it has to be accessible, right? So your data scientists have to be able to access this data to do the things they need to do for it. It's often harder than you think. So that means that you need to have the infrastructure in place to collect the data and to make it easy available to the people who need it. So I'm not going to cover how to do that today, because again, it's a huge topic. But I will say, take a look at our just released Data Pipelines Playbook, which has got lots of good practice and experience that we've had in getting data for not just for machine learning, but also for BI and other kind of activities. It's a great playbook. Go and see it. Go and read it. I want to focus now on the major pitfalls that can happen when using AI, some classic things, and suggest some practices that you can put in place to make sure they don't happen to you. I'm going to start with explainability. So in many situations, being able to explain how your algorithm has reached a conclusion is important, and can be in fact a regulatory requirement. So some approaches are easily explainable and some aren't, and there is a fundamental trade-off. That's what this arrow here is trying to show, between explainability, how easy it is to understand how you got a result, and performance, you know, the accuracy effectively of the algorithm. So if we look at the simplest approach, which is a rule-based system, everything in a rule-based system is a set of if-then rules, and it's understandable by pretty much anybody. You know, you just have to follow through the if-then rules. This here is taken from something called Drools, which is a current open source system for rules-based systems. And of course, you have to create and maintain all the rules, and the rules are usually much coarser, so they'll give a lower performance than other methods. The next level of sophistication is statistical, so something like this here, and you're using stats effectively as the core of your algorithm. So, you know, here's an example here of, you know, let's say you wanted to do pricing. This is actually the pricing of spruce wood against the volume of salvage logging. Maybe you've got a spruce wood timber merchants or something, and you want to understand what a good pricing strategy would be. And this is, you know, this is just straightforward regression line here against those points. And again, that's very understandable. It's very clear how it reaches that conclusion. Anyone who's got training in stats can understand it, and many other people as well. Although of course, some statistical models can get very complex indeed, and can end up harder to understand. But when we move on to the more advanced techniques, such as some of the more advanced kernel bases in machine learning, or the kind of deep learning neural network, deep learning approaches, it's much harder to explain how an individual decision has been reached. So this picture here is a diagram of a pretty simple neural network, and the way it works, for those of you who don't know, is you put your data on the left-hand side here in this input layer, you get results here in the output layer, which kind of either state what class it is or provide a regression value or something like that. And in the middle, there are these hidden layers that effectively process the data. And you can see, even with something like this, it's pretty complex to work out why this is, for example, it's chosen this middle neuron here as the class it's in. It would be, you have to work through all these different kind of connections here. It's very difficult to understand what's gone on. And this is actually a pretty simple neural network model. The deep learning ones that you use for machine vision and things like that are many more layers deeper than this. So you can see how difficult it would be to explain why, for example, credit was declined using this. Okay, so let's talk about bias now. I'm sure many of you have heard about the problem of bias in AI, and many of you may well have heard this example here from Amazon. So Amazon created a tool for streamlining recruitment, which ended up being biased against women. I'm sure they didn't deliberately create an algorithm to do this, but what it used their previous hiring examples of the data, and there was biased approach in that effectively. So the algorithm effectively encoded the previous biased practices and applied them consistently, and so the tool had to be scrapped. And this happens really quite frequently. Another example, I think it was the New Zealand Passport Office created a photo validation tool. It's a good idea. You send these photos in for your passports. Why not have a tool that says, yes, that one's likely to be correct for a photo. No, reject it, go and get another photo. Unfortunately, this tool rejected people of Asian descent for having closed eyes. And obviously what happened was that the training set was not representative of the data when in operational use. There was a bias effectively in the training set, which meant it couldn't be used. It wasn't fair for the population. If the biases in your training set are too great and you don't recognize them, then you will end up with an algorithm that doesn't work for some parts of your operational data. So you should strive to find data that is representative of the target set. So that means it fairly covers the classes that you're modeling. It's big enough size for the sorts of classes of interest you're going to meet. It's up to date and it's relevant. For anything working with faces or something like that, and then you've got to make sure that your algorithms are tested on different ages and races and sexes. The ICO, the Information Commissioner's Office, has been looking at the challenge of bias in AI and has put out some helpful guidance. In fact, in general, the ICO has been putting out quite a lot of, I think, quite useful guidance around applying AI. I mean, they're interested in kind of bias as a fairness thing more than a performance thing. But one of the things they said that if you ignore protected characteristics, so that's things like race and religious belief and sex and things like that, and you're making a decision that ignores those protected characteristics, then you're likely to be protected against bias. So you won't be biased in terms of things like the decision making. Okay. Next, overfitting. So overfitting is always at the back of the mind for anyone developing or deploying an algorithm. I'm sure Thorben, Paul, Mike, and lots of other people on this call will know about this and worry about this from time to time. And it's when your algorithm doesn't just learn what it's supposed to learn, but it also learns the noise as well. What you want to do is you want to learn the underlying function, not just learn the data exactly. So the three graphs here show a simple machine learning. It's a polynomial, or three different polynomials for a simple underlying function. So the red line is the true value. The red line is the true underlying function there. The dots are the sample data points that we have observed. And you can see there's some noise in our observations. It's very common in data that you get noise in the observations. The blue line is the approximation that the different machine learning approaches have made. You can see that this middle algorithm is a good fit. It's a really good fit, but it's not quite on all the data. You know, there's some differences there. And the right algorithm, the right learned function, actually is much closer to the data points, and the error on that from that data is going to be lower than the error on this one here. But of course, I think we can see that, you know, this is the true function here. This is the true approximation, and this one isn't. And this is kind of fundamentally what the worry is in everybody's heads when they're making a machine learning algorithm. It's, have I done this? Have I actually just kind of modeled the data too much, or am I actually getting close to the true function? And there are things you can do to protect against it. You always have to keep a test set, as I said, for evaluating your algorithm, which doesn't have the training data. You can do cross-validation, which is where you're kind of sort of running it lots of times with different parts of the data as the test set. You can look at simpler models, so bias it towards simpler models here. So this sensor version is a simpler model than this one here. It's got less kind of it's a polynomial of order 4, as well as kind of trying to minimize the number of variables that you use. Are all good kind of techniques you can do. You might ask about underfitting about this one here. That's not much less of a concern because you discard that anyway. This would have a lower error than this, so you discard it anyway. Just one thing to point out, I guess, is it looks quite simple here, but in most cases, the functions you're trying to learn are much more complex than this, with many more variables. So it's kind of harder to spot. Okay. Next, I'm going to talk about sensors. So in robotics, sensors and sensor processing are some of the main challenges. What do I mean? Well, we've got two examples here. In the first one, an emergency braking system mistook a cattle grid for a wall. So it's something about the reflections from the sensors, rather like a radar, LiDAR, vision, you know, optical cameras, not really sure what they were, but something about the reflections of those on the cattle grid made it look like a wall. It made it look like it was up like this. And so the onboard processing system made the cars swerve off the road. The second one here is a 5-foot tall security robot, which ran over a toddler that was trying to play with it. Fortunately, the toddler was not badly hurt. But obviously what happened there was that the sense and avoid algorithm that was working in this robot had not been developed with the shape and the movement of a typical 2-year-old, meaning it either didn't see they were an object or it didn't treat them as something to be avoided. So overcoming these sorts of problems is one of the main challenges that any robotics solution has to face, and one of the difficulties that autonomous vehicles are still trying to overcome, particularly in complex environments like towns. And really, you know, you have to collect sufficient data for all the conditions that you expect to operate in. There are always lots of edge cases, so cattle grids, small children, snow, hail, whatever, which you have to collect and learn from and add to your algorithm. Unanticipated behaviors in production. Oh, I see what the time is. I'll try and just move up the pace a little bit. So this seems to happen a lot with chatbots. You may well be familiar with this example here. Microsoft developed a chatbot called Tay. It was great. It was really good, a really good piece of software in a lot of ways. It's very natural in its conversation. Unfortunately, they deployed it without taking into account the horribleness of people on the internet. And the chatbot went from this kind of, hey, happy-go-lucky, you know, 10-year-old, why isn't it National Puppy Day every day, to it's saying, do you support genocide? I do indeed, within a 24-hour period, and significantly worse. And they're not the only ones. Tencent had one that they had to shut down. Doesn't just happen with chatbots. So Facebook does this thing where they auto-generate advertising categories. They didn't check what was being generated, and that led to some deeply unpleasant categories. You know, you've got learning from the internet. There's a lot of horrible people out there, or people who are really trying to kind of make things not work. So how do you protect against this? Well, you know, what's happening here is you're deploying an untested algorithm straight into production. So you're training it in production. So you really don't have control over how it's going to behave. and you can't detect and prevent those bad behaviours. Okay. Last of the pitfalls here. AI, as said, uses data, and like anything that uses data, it needs to be respectful of data of a protected nature, PII or other protected characteristics. It has to be bound by the rules that all data processing systems must follow. On the left is an example where it wasn't done right. So Google developed an algorithm. This is DeepMind developed an algorithm to detect kidney injuries. Very laudable thing, right? Better detection rates, maybe earlier detection rates, but it didn't meet the rules for data protection. Among other failings, the ICO said the hospital did not tell patients enough about the way their data was used as required by the Data Protection Act. I'd like to say, right, on the other hand, you can get it right even for very tricky use cases. So on Fido, a company that make like personal identification software for things like anti-money laundering, know your customer, when you join a bank, that sort of thing. Very clever software. Obviously, this is protected data, right? It's personal, there are biometrics, and there's a possibility of bias if it's not done well. So they worked with the ICO, and the ICO has what they call regulatory sandpits for difficult cases. And I think that, and managed to get the product out in a way that met the kind of legal requirements for data protection. I think it's a really great example of that you can do it well, and that the UK regulatory authorities are keen to make things work and to allow this area to develop whilst keeping our data protected. Okay, so hopefully I haven't scared you off with all the pitfalls. Most of them, if not all of them, can be addressed by adopting the right practices in the workflow. So if we go back to my original workflow diagram, with your data, make sure you're following guidance on using AI and you're following data protection laws. Take a special care if you're using special category data. ICO has some good guidance actually around this that's worth looking at. Make sure that your data is representative of the things you're trying to train. When you're in that kind of model development, algorithm development phase, understand if you have a requirement for explainability and select based on that. Make sure you validate the performance appropriately, using unseen data, cross-validate, do all the things you need to do to prevent overfitting. Do validate your behaviors before deploying, so you don't end up with a system that's out there you don't really know what it's doing. And then when it's in operations, continue to monitor the performance and capture those edge cases that come up so that they can be folded into the next iteration of the algorithm. Thank you for listening. Hopefully that's been useful. I'm going to hand over to Sam, I guess, to run the Goldfish panel.
That's right. Thank you very much for that, Simon. Would you mind just stop screen sharing? Lovely. So we can see everybody. Great, that was really interesting. Thank you, Simon. We have got a question in the Q&A, and I'm going to just call out if people have any questions. Don't be shy, just ask us. But I'm going to start by taking advantage of my position as host to ask you a couple of things. I'm going to go straight for the toddler question. So, it seems as sort of, somebody who doesn't do ML or any of the data stuff, it seems so obvious, doesn't it, that you build a robot that's going to be in supermarkets and areas where there are toddlers. That would be something you would do, but obviously it's not that simple, is it? And so how does the sort of data that builds those sort of edge cases get gathered? How do we deal with sort of gathering enough information, enough data that you can do those sort of tests to make sure you're doing the right thing? I'm going to ask you, Simon, to start with.
You're going to ask me to start with? Yeah, sure. So it's a great question, right? And it's a real challenge. And, for the autonomous, we talked about autonomous cars. That's something that they are really struggling with, is getting hold of the sufficient amounts of data that you need to validate the system performance. And so a lot of what they're doing there actually is in virtual environments, right? Okay, because the thing is, it's behaviors and stuff like that you're trying to know. And so they're speeding up their kind of validation effectively by running things in virtual environments, which means you can run many more than you can with the traditional approach, which is driving a car around a track or whatever. which would take millions of years to get all the data that you need.
Thank you.
Well, one of the intrinsic problems with the toddler situation there is that it's there's a lot of data which are edge cases in which you typically don't have very many representative examples of in your training data set, and so many of the things that cause difficulties are in that edge set, and you need to make sure that you have a very diverse set of example cases, including a disproportionately high number of what you would consider to be edge cases.
One way you can achieve that, that's just been talked about, is really just making sure you have diverse teams. I mean, probably the team that worked on that robot maybe was all, men of my age and younger, and just didn't think about toddlers. Whereas perhaps if there'd been a mum on the team, it would have been the first thing she thought of. So a simple protection.
Interesting, yeah.
Yeah, it's worth remembering how long humans take to learn to not bump into things and fall over. And, we have many thousands of hours of exposure to constant feedback. So it's reasonable to expect that although AIs and robots can learn these things much faster and then, take what they've learned and just, make a copy of that for the next robot, it's definitely not a trivial thing to do. And I think it's still a very actively researched area, stuff like embodied computing, where we realize that actually having a physical body is quite different from just designing the brain for the thing. And even aspects like shape and how you respond to being in an environment has a big impact on our understanding of intelligence. So I think there's a lot of work still happening in that space.
Brilliant, great answers, thank you. So one of the questions from before the talk that we're going to ask you is, so sort of following on a bit really, but how much data do I need? People, we talk about big data, which is a bit marketing in some ways, but I mean, how do you know when they've got enough?
I can say a little bit about that if you like.
Okay.
I think as much as possible would be a flippant answer to say, but it depends really on what algorithm you've got and what base you're starting from. So I would typically start with a small amount of data and see whether see how well my chosen algorithm works with that, and then try increasingly more data and see what the trajectory of the improvement is, and you can kind of extrapolate a little bit from that to work out what you might need. But in the case of things like deep learning, you might need thousands, if not tens of thousands of examples of data to get a decent amount of learning. And so you tend to turn to other techniques. There's a technique called transfer learning, for example, which is where you take a model that's already been trained on a huge image data set. There's a thing called ImageNet, for example, that has 200 classes and tens of thousands of images. That you can take an example, a model that's been built for that, strip off the top of it, put your own top on it, and just retrain those little top layers to deal with the tiny bit of data that you have got. So it's effectively giving you a boost of having, it's as though you had tens of thousands more examples than you actually have. So that's one approach. And plenty of online databases too. If you don't have enough data yourself, there's a little known resource that Google have called, I've got it written down somewhere, called the data. If you look for datasetsearch.research.google.com, I'll put it in the chat later. That's like a search engine for data sets, and you can find all sorts of crazy things about health and cars and animals and people and gestures and all sorts of things that you might be interested in.
Brilliant, thanks, Mike. I'm going to move on to another question, and Paul, I'm going to ask you this one. So when have you seen AI used well, and what successes have you had?
Sure. All right. Well, thanks for asking me that one, because I thought of an example. About 3 years ago, I was working with a fashion startup, and they had a little app. and you could take a photo of yourself in your clothes, obviously in your clothes, and then you could kind of go to the retailer's website and tag all the clothes you're wearing in the photo, and people could go and buy them, that kind of idea. And this process of tagging the clothes took ages. We looked at our metrics; it was taking 40 to 60 seconds for the people who actually finished the process. Most of them just stopped halfway through. And what we did was we used Google's machine vision. We just had this idea of taking photos of barcodes, taking photos of the price labels on things. Barcodes are proprietary to the retailers, and then just doing text recognition on them to try and find things that look like product IDs. That took us like 3 or 4 days to implement because Google did the hard work of building the machine learning model. We just used it. In our sort of first trials of kind of putting that into production, we let people sort of say whether or not it works for them, so we could collect some data and some feedback that way. And we got great feedback. We could see the people for whom this was working, as in we're using the retailers that we've done it for. They were basically getting almost perfect responses every time, and it was done in a second or two, and the process was awesome, not tedious. So yeah, I was really happy with that. I think definitely one for use someone else's model and just take the credit.
Brilliant. Well, Torben, do you have any examples of successes that you've had using it well?
I mean, I can think of, many established use cases in industry stuff like recommendations engines, which are just, so commonplace now that people don't even think that that's AI anymore or machine learning. It's just something that every website that sells stuff does. So yeah, implementing those sorts of things, you can pretty much apply sort of out of the box techniques and get really good results. Other places are things where companies had loads of natural language that was available in terms of product reviews, or maybe in sort of polling results, where you could easily use new AI techniques to summarize those and kind of extract insight that would have been a difficult manual task before.
Brilliant, thank you. We've got quite a few questions. I'm going to move on if that's okay, unless Simon, you're burning to tell us a success you've had recently.
We've had lots of just one I want to raise, right? And it's quite a simple one, but it made an awful lot of impact for our client, which was about, they had a whole stack of documents, PDFs, right? It's exactly that case, right, with lots of kind of untapped data in there. And we provided a tool that, enabled them to extract entities and things like that from that data, from which they achieved, hundreds of millions in terms of value effectively for them.
Brilliant.
Simple tool, applied in the right place, lots of value.
Yeah, brilliant. Thank you. So I'm going to move on to a question from Michelle, which is, what is the current view? What is the group's current view of Financial Conduct Authority on ML, please? She's recognizing that 2 or 3 years ago there was a bit of a no-no owing to issues with explainability.
Paul, did you want to jump in? You had your mic open there.
Only if nobody else was. I had a tangential brush with it a little while ago, but if you've got a proper answer, that'd be better.
Well, what I was going to say is I don't personally know the current view of the FCA, but usually credit risk scoring, for example, is one of those situations where explainability is required, and that's fair, right? And I'm pretty sure if I check the regs right now, you'd have to say, yeah, it has to be explainable. So I doubt that that's changed, and it's not just in the UK, it's all over most places. And that's about, so going back to that, sort of model selection, if you choose a rule-based approach, that's very explainable, so you can apply that.
Yeah, I guess the only thing I'd add is that explainability is coming on leaps and bounds in domains that demand it, right? The regulators create the pressure, and then the creative people step in and create solutions. I was aware of a company in my home city that was working in, I think it was credit scoring, basically using a machine learning model with some constraints to make it explainable. And as far as I know, that product, it was used in production, so they solved the problem that way. But there may be solutions out there, basically, but the requirement is still there, as far as I know.
Brilliant, thank you. Another question from before the talk was, how do I know when my model has overfitted the data?
I'm happy to take this one. Well, I guess
Thank
that's the crucial practice of splitting the data you have into a training data set and a test set and a dev set or validation set. So you never show the model while it's training or learning the things you're going to test it against, and you make sure that the test data is representative, so coming from the same sort of statistical distributions as the training data, and then you see whether the things it's never seen before it can answer questions well on. And typically during training, you'll see that it gets better and better and better at answering questions from both the training and the test data sets. And at some point, it stops getting better at on learning about the test data set, but still goes on learning about the trained data set. And that's probably a sign that you're overfitting. There are other kind of overfitting analyses you can do as well.
Brilliant. Thank you, Torben. Does anybody else want to chip in after Torben?
Yeah, I'd just say that, that the mechanisms that Torben's talking about are these days automatic in most of the training libraries that are out there. So you usually set a thing called early stopping. So you have a system that is monitoring the training and checking that the validation score is getting better and better. And when the validation score starts to fall off, even though the training score is getting higher, when the validation score starts to drop off, you call a halt to training and rewind back to the model as it was at its best a short while ago. And that's usually all automatic. So there's not really a great deal of thought these days that has to go into that. It's sort of a one-liner in Python.
Lovely, thank you. So a very specific question from Pratap, which you might need to read. So I'll read it out because it sounds like a very real problem someone has. How do you go about creating a data set for training a model that could be able to generate natural language text based on structured JSON input, which describes a simple bar chart? I'll give you a moment to think through your mastermind answers.
Well, first of all, have a lot of examples. An awful lot of examples. You can also do cunning things where you do it in reverse, where you say, if I've got one, can I create the other, and then can I use that to train the opposite way around? Anyway, that's probably more an offline discussion.
Lovely, thank you.
So GPT-3, and Mike probably knows more about this than I do, but I know that people have used GPT-3 for automating programming. So you describe effectively what you want your how you want your user interface to be, and it's generated an interface. Okay, right. So it's generated the code to create that user interface. I don't know whether there's some way of kind of taking something like that and reversing it around so you can go from what the graph looks like to effectively a visual description of it. I don't know.
Yeah, well, I've definitely done that using GPT for a description of a web page, for instance, and then spitting out the code for it, or even code-to-code translations, things like saying what you want from data and it generates a SQL query. So those things are kind of possible, but I guess in terms of generating a training data set for this, one option not to forget is it's really easy to generate the JSON that you want, and presumably you have some library that can draw the graph. You could then use crowdsourcing to get some labels and say, what is, depending on how much cache you have, like type in some words describing what this graph looks like, and you know what the input looked like. So there are ways that you can create your own test set relatively easily for this kind of case.
That's very creative. Thank you, Torben. So I'm going to move on slightly to a slightly different area. So question from Ryan Sikorski. How often and when do you need to update your model? And how do you build it to take into account changes? So double question, really. Cool.
Yeah, I take a stab at that to start with. It depends on the problem that your model is solving for you, I guess. I mean, if you think about, I remember working with somebody who built a propensity to contact support model. So for all the customers of the company, trying to predict if they were going to contact a support line. And really the model's predictions didn't really change very much from I think it was being trained every day. That didn't really change very much. But a machine learning model that works in a driverless car, for example, that's trying to figure out and not to kill anybody, might need to be constantly retraining itself in the real time. So it's very much a kind of a domain specific thing. But as a general rule, I think kind of starting with daily is probably a good starting point to. If that's what I would start, is like, why wouldn't we do it daily? Would be the question I'd ask.
I'd say that gets more difficult if you have models which take, might take weeks to train. But it's really important in production to have monitoring and alerting in the same way that you would for normal code that you write. Often it's difficult to have a measure for how well a model is doing in production if you don't have some baseline test cases that you're testing against. But if you can see whether the sort of metrics you're looking at for, I don't know, conversion or something like that are falling, the model is not performing as well as it did before, that might be a sign that it's time to retrain, that something's changed about the environment in which the model is supposed to be working. A great example is in retail, for instance. Searching for chocolate around Easter should bring different results for searching for chocolate around Christmas or Valentine's Day, right? And if you start off with a really simple model with just a little bit of data that you gathered around Valentine's Day, then you don't expect great results at Easter, and you'd see that in the performance results, and you'd have to see, okay, I need a bigger period of time to be able to create a model that is time specific as well.
Lovely, thank you. So I'm going to just do another two questions sort of together, really, because they're to do with production. So, yeah, first question from Nathan: what do you most often see as the biggest impediment to getting modelers into production? And then on top of that, sorry, I've just lost it. And from an outside quarter, what kind of things would you be monitoring in production? In addition to biases. So the first one about how to get things into production. The second one about what you're monitoring in production.
So I mean, it's a really good question. I mean, there's you can quite often get these situations where you've got great data science teams doing great models, great algorithms, but then don't end up anywhere, right? For a variety of reasons, right? And it's very frustrating for them, and it's very frustrating for the people who are making the investment in these models. And it can be because they've been created in a way that it's just not easy to integrate them into the operation systems. It could be that the people in the operation systems just don't have the bandwidth to integrate them, because in the end, what you need to do is to bring that algorithm into your normal operating systems, and that's just a software engineering task in a lot of ways. But we see that, I think, quite a lot. That's part of the challenge of what people call ML ops. It's it is bringing that model into production, but often it'll be the format that the model's in, it'll be the bandwidth that the people are able to integrate into operational systems. It might be the data flows. You have data flows in the development environment that you don't have in the operations environment, and there isn't the bandwidth to create those data flows in the operations environment. Those are the sorts of things that I see.
But there can also be an issue of having excessively high expectations of an ML system. So Simon and I worked on a system for a client who shall remain nameless, where we had to produce images that had to be pixel perfect, because humans could do what we were trying to do in a pixel perfect manner, and we were just a tiny little errors here and there. You'd have to have zoomed in on the images by 1,000-fold to have seen, but still that gave some pushback for acceptance into putting the effort into putting it into production.
Right. Thanks, Mike. Yeah, that must have been very frustrating. We're nearly at the end of our time, actually, so I've just got time for probably one more question, and I'm going to take a question that Tom Bianco's asked, which is, how do you approach classification and validation of a problem to determine what level of complexity is most suitable to address the challenge? And by complexity, it means, for example, rules, statistics, and regression.
Well, I think that's a really good question. Like, really goes to the heart of the first question people are going to be asking, right? When you look at using these things in reality. For me, like, the first question when somebody says I want to do ML is what have you tried that's not machine learning? Because if you can solve the problem without machine learning, you should do that. It's kind of like the top end of effectiveness, but also kind of complexity and specialism in terms of the skills that you'll need to support and maintain these things, I think. Others on the panel might disagree. But yeah, it would be like, can you think of a way of doing it without machine learning? Machine vision, natural language processing, those sorts of things. No, can't really think of a way of doing that. But modeling, modeling a Boolean AND gate, yeah, we can probably do that with a rule, and it'll be fine.
I mean, I'd agree with Paul there that it's as simple as you can, right? It's simple because complexity is always extra cost, and you may well overfit whatever. But definitely, the simplest approach to do. And if it's a statistical approach, if simple regression, then that's fine. Sometimes I get clients kind of sneaking up to me and saying, I've got a linear regression, and I don't know, should I be doing something more complex? But if that's meeting your job, if that's meeting your needs, then absolutely linear regression is perfectly fine.
Yeah, I'd also add that you start with what you've got. It's very rare that you would have all the data you need available right away, or know where that is in an organization, or have it in the right format, or it be accessible in production. And you kind of have to start simple with the things that you have, and hopefully can build something that proves the value of the approach you're trying to do. And it can get more complex later if you can squeeze more accuracy out with a more sophisticated model or something. So yeah, I would treat it like a normal software problem and look at what you have, what you need to build, what in terms of business analysis for requirements like explainability. If you had a team of people doing this instead of an AI, what would you be able to show? How did they make the decision? Those sorts of things. You can ask those same questions and use that to sort of guide the shape of the thing that you're building.
Brilliant, thank you. So we are at the end of our talk today. I would just like to thank all of our panelists, Simon, Torben, Mike and Paul, for joining us and talking to us in such detail. I must admit, I'm personally feeling a lot safer about the idea that autonomous vehicles are going to have the right level of data testing going on behind them if you guys are around to do that. So thank you again. Our next talk is on Wednesday next week, May the 19th, 8:30 in the morning UK time, 5:30 in the afternoon in Australia. It's entitled HMRC Going from a Data Storage Team to a Data Product Team, with Andy Leatherby from HMRC in the UK and Scott Cutts from Equal Experts. You can register on the link there. I'm sorry we didn't get to all the questions. There were so many. But please join us next week to talk about HMRC. Once again, thank you for our panelists, and of course, thank you to everybody who joined. I hope you found that a useful conversation and a useful session. Thank you very much. Goodbye.